All right, so today we're going to talk about the comparison tests. As I was mentioning before, I gave a preview of this in the last section. We're going to talk about two types of tests. Firstly, the comparison test, and then secondly, the limit comparison test, which I just said was very powerful. So, the comparison test, we had a taste of this in sequences, and the idea is if you can compare one sequence to another sequence where you know a relationship, like one is always smaller than another or one is always bigger than another, then sometimes you can use the convergence of one sequence to tell the convergence of another sequence. Or we can use the divergence of one sequence to tell the divergence of another. We're going to use that same idea with series rather than sequences. So, here's the idea. The idea is we're going to compare one series to another series that we already know the convergence for, whether it converges or diverges. Typically that's going to be like a geometric series, or it's going to be like a p-series. You guys, do I need to write that down, or you guys got the idea? Do I need to write it down? Okay, I better write that down. So here's the idea. Compare one series to another where you already know the convergence or divergence. Typically, this is the series that we've already talked about in this class, like a geometric series, or a p-series, or a harmonic series, something like that. So here's where the comparison test comes in. It says, all right, so suppose we have two series. We have a series of A sub n, and we have a series of B sub n. And both of these are series with positive terms. So suppose the series of A sub n and the series of B sub n are series with positive terms. Well, there's going to be two cases, and I'm hoping that you see the similarity between this comparison test for series and the comparison test that we had for sequences. So here's the idea. Let's suppose, or let's say A sub n is less than or equal to B sub n for every term. So basically, here's what we got. We got these two series. They both got positive terms, but here's what we know. We know that the series of A sub n, every term, the sequence of that basically, every term by term, A sub n is less than B sub n. So for the first term, A sub n is less than or maybe equal to B sub n. Next one, A sub n is less than or maybe equal to B sub n. And so forth, and so forth, and so forth. So basically, if I have my B sub n like this, my A sub n is right below it or maybe equal with it, but it's never above it. Do you guys understand that idea? So term by term, A sub n is less than B sub n. Quick hit on if you're all right with that. Let's further suppose that B sub n, that series, converges. What's going to happen? What's going to happen if I have my B sub n's and I have my A sub n's? And I say, hey, tell you what, they're both positive terms, so they're both above 0. And I say, for every single one of these terms, A sub n is less than, or maybe equal to B sub n. It could be right on top of it. Who cares? It's just not greater than that. I say, furthermore, what I know is that this series, when I add all these terms together for B sub n, this series converges So if the series of B sub n converges and A sub n is always less than that, but it's never negative, right? It's always positive. So it's bounded and it's less than the series that's convergent. What's going to tell you about this the series of A sub n? What's going to happen with that? It has to be. So here's what the comparison test says. It says compare one of your sequences to another one where you know the convergence for. There's going to be two scenarios. The scenario is going to be, well, if A sub n is always less than B sub n, if B sub n converges, if the series of B sub n converges, where add all together goes to one number, then if A sub n is always less than that, it also has to converge. Okay, let's see if you're paying attention. I know some of you guys look like you got sleepy eyes, so let's focus right now. So now let's do this one, okay? Check up here, eyes on the board. Now let's suppose that B sub n diverges. If A sub n is always less than B sub n, and B sub n diverges, what does it tell you about A sub n? Why not? It's below it. Well, A sub n is below the B sub n. So if B sub n converges, yeah, if A sub n is below it, it's also got to converge. That makes sense because it's kind of pushing it down here and getting closer and closer and closer to one number. If I add those together, when we're talking about the series, now not just the sequence, but the series. So if the series of B sub n converges and A sub n is always below it, then the series of A sub n also has to converge. But if the series of B sub n diverges and the series of A sub n is below it, it tells us nothing. A sub n could diverge, it could converge, I don't know, because it's not being forced anywhere. This idea of the series of B sub n converges and A sub n is below it, the series of A sub n is being forced somewhere. It's being forced down and down and down and down and down. If B sub n were to diverge, A sub n would not be forced anywhere. It could go either divergent or it could go convergent. It would say nothing. Show of hands if you understand that idea. Okay, what's it going to take? What's it going to take to show that a series would be divergent? What would have to happen here to show divergence?
B sub n has to be less than A sub n.
Oh, it's, hang on, two people talking. Go ahead.
A sub n will have to diverge to show that B of n is divergent.
Okay, I'm going to state it as A sub n is being compared to B sub n. So let's say that right now B sub n is going to converge. We already did conversion, didn't we? Let's talk about B sub n diverging. So let's say that B sub n is going to diverge. With A sub n being below it, does that show divergence?
No.
Where would A sub n have to be in order for B sub n to diverge, and A sub n must also follow suit and diverge? Where would it
Above
be?
it.
It's got to be above it. So that's our next case. So if A sub n is always bigger than or possibly equal to B sub n for all n, and the series of B sub n diverges, well, then the series of A sub n has to diverge. Here's this case. It says, all right, so start off, suppose that that for every single term, here's B sub n, A sub n's a little bit bigger. Here's B sub n, A sub n's a little bit bigger. Here's B sub n, A sub n's a little bit bigger. So every single time. Well then, A sub n's not here anymore. A sub n says, no. I'm always just a little bit bigger. Now I'm up here. Term by term, I'm a little bit bigger. Now suppose this. Suppose that the series of B sub n is divergent. So this thing diverges. If A sub n is also a little bit bigger every single term, if this thing adds to infinity, or diverges or something, the series adds to infinity is going to diverge, and A sub n is a little bit bigger, where's the series of A sub n going to go? It's going to be bigger than that. Since it's term by term bigger, if I add up all these terms and it diverges, then if I add up terms which are slightly larger than that, it's also going to diverge. Show of hands if you understand that idea. So now let's do this one. Let's say that B sub n converges. If A sub n is a little bit bigger and B sub n converges, what's it tell you about A sub n? Nothing. It says, hey, this one's bigger than that. Great! B sub n converges. Okay! What's it tell you about A sub n? Nothing, because A sub n's bigger. It could converge, I don't know. It could diverge, I don't know. It's not being forced anywhere. With B sub n diverging, it forces A sub n to also diverge because A sub n is larger than that. Show of hands feel okay with that idea. Would you like to try some examples? Do you guys see the similarity in what we did between our sequences in this? It's really similar. It's just a series. Just had to make a statement here. So let's try a few examples. Are there any questions before we get going on? And hopefully it's going to be pretty straightforward. So let's try one. Let's really see if you're with it today. By the way, what's the first thing we should always check with series? No matter what, first thing, what would you? We should always check that because it's going to be really quick. So let's do the divergence test. Does that diverge? Okay, that's a horrible way to ask that question, actually. Are you certain that it might not diverge? That's a weird way to ask it. Does it pass the divergence test? So basically, is the limit equal to 0? If it wasn't equal to 0, what would you know about this series? For sure. So it might not be divergent, is basically what you know. Do we know it's convergent yet? No, we don't know that. But we know it might not be divergent because the limit of our sequence from which our series is built equals 0 as n approaches infinity. You okay with that one? Okay, so we check that first. Nextly, we go through our progression. Is it a p-series? No. Would that be a p-series?
Yes.
Okay. You sure?
Yes.
Yeah.
Okay. Say what now?
When p is greater than 1.
When p would be greater than 1. So we know something about that, but this is not. Now, later on, we're going to compare this to something very similar to that. How about integral test? Could you do an integral test with this? You actually could. It'd be hard to do because that's not a perfect square, but you could still do it. You could do an integral test with that. It's going to be some form of like a tan inverse, okay, if you were to do that. Not such a big deal. You could do that. Is there an easier way to go about it? Yeah. Here's the easier way to go about it. Let's compare this to a series that we already know the convergence for. So basically, here's what we need to know. Firstly, we need to say whether these terms are all positive. Are all these terms positive? Yeah, okay. So we know that because all these terms are positive, this is greater than or equal to 0. And now we're going to base this on something that we already know the convergence for. If we're trying to show, listen, if we're trying to show convergence, you need to have this as less than something, some series where you know convergence for. If you want to show divergence, you need to have this bigger than some series you know divergence for. It's silly to have something less than something divergent or bigger than something convergent. That doesn't show you anything. So what we're going to do is go, okay, does that look like anything familiar? And you guys just said it. You said it looks like a p-series, doesn't it?
Yeah.
Let's make this less than the p-series. Is this true? Is that true for all n greater than 1?
Yes.
Yeah. Well, we know that when a denominator gets larger, our fraction gets smaller. So this fraction would always have to be less than this fraction. You still okay with that one? And this is true for...
All in.
Yeah, as a matter of fact, it's true for all n, but we only need it greater than or equal to 1. So let's go back and see what this says. This says we're always going to have positive terms, no matter what. This says that, well, this is a true statement. We're basing this on something we don't know the convergence for right here. This is a p-series. That's fantastic. Well, if that's a true statement, then here's what the comparison test says. It says, well, do you know that convergence for this?
Yes.
Okay, let's go through it one time. What's that called again?
P-series.
What's the p here?
2.
So we know that this is a p-series. P equals 2. Hey, that's greater than 1. That's fantastic. We know that if p were less than or equal to 1, we'd get the harmonic series or something below that, and we'd get something that would be divergent. Actually, above that, as far as sequences go, we'd be divergent. So here we know, hey, it's a p-series. Not a problem. P equals 2. That's more than 1. Therefore, this series is what?
Convergent.
Now we're going to put the whole thing together. Put the whole thing together. We start with some series. Yeah, you could do a couple other tests with this. Not a problem. Can we do a comparison test? Well, that depends. Are all your terms positive?
Yes.
Yeah, it says right here you got to have positive terms. So all our terms are positive, no problem. Is it less than a series that you know is convergent? That's what you ask now. Is it less than a series you know is convergent? Or is it bigger than a series you know is divergent? In our case, I know that this thing is less than 1 over n squared. It has to be that way because I'm just taking my denominator and adding 2 between this fraction and this fraction, between this sequence and this sequence, or likewise our series and our series. So these are always going to be less than these terms for every single one. Term 1, term 2. It's always less than that. If it's always less than our sequence we know is, our series we know is convergent, well, then we got to look at that thing. The series of 1 over n squared is a p-series. We know the p is equal to 2. That's more than 1. That shows convergence. So what do we know about this series as well?
It also converges.
That also converges. So, our series of 1 over n squared plus 2 also converges. I want to make sure you guys really understand this before we go any further. Did that make sense to you? Show of hands if you did. Feel okay with that. So basically what we're doing, we're comparing one series to another. We're comparing it to make it, to show whether it's convergent or divergent by saying, well, if it's below one series that converges, our series converges. If our series is above one series that diverges, our series diverges as well. That's the only two scenarios that we can really have. There's only two cases. Have I explained this one well enough for you guys to get it? Can we move forward? Okay, let's try a couple more. Let's give this one a try. Let's start from the very beginning with all of these series, really go through the progression. What's the first thing that we try anytime we get a series and we're trying to show convergence or divergence? What do we test first?
Divergence.
Okay, so we're going to take a limit of this thing. Does the limit of this thing equal 0?
Yes.
If it didn't, we'd stop right there. If it does, hey, we're good to go. Let's continue with this thing. So it says, hey, the limit of the sequence goes to 0. That means that potentially we could be possibly not divergent. We got to show that, though. We can't just stop right there. It doesn't show convergence. After that, man, we go through our list of things to do. Could we do integral tests? I don't know, maybe. But it's probably a little bit easier to do a comparison test right now. Here's why I see that. First I see, are my terms positive all the time?
Yes.
Okay, well that's one condition. We got to have that for comparison test. So I know that we have all my terms are positive. Second thing I'm thinking about is this. Can I show that this is either greater than some series which is divergent or less than some series which is convergent? Can I show that? I don't know. Can you show that? I can show that. I know how to do it. Here's what I'm thinking. I'm thinking that the one thing about this is that 3 is kind of holding me back here. Does that make sense to you? So the reason why the comparison test is so nice is if you haven't noticed this already, it allows you to get rid of little pieces which are holding you back. So you go, hey, that plus 2 is holding me back, man. Let's get rid of that. Well, if I have a plus 2 in my denominator, it's going to be less than 1 over whatever I have without that plus 2. Does that make sense? Now here's the little kicker for you. What if it was a minus 2?
Ooh, greater than.
Yeah, that would be a problem. Because here, that would be a minus 2, and that would be a greater than. Okay, stick with me here. I'm going back to this example. Now, look. We know that this series converges, don't we? But that series is bigger than that. So this double inequality makes absolutely no sense. It says this is bigger than 0. Okay, this is bigger than that. So I can't use a squeeze theorem if you're thinking squeeze theorem right here because I don't have my double inequality set up the correct way. This says, all right, those are positive terms, fantastic, but now this series is bigger than this one. This one converges or diverges?
Converges.
Tell me something about a series which is bigger than a convergent series. Does it tell us anything?
No.
That would be a problem. We'd have to do something different with that. But if we have the plus, man, we're all set up. We're good to go. We're good to go. In our case, do we know that this is less than or equal to some series? Less than what?
1 over 2 to the n.
You know, I mentioned the squeeze theorem about 5 seconds ago. Do you guys see that essentially we can use a squeeze theorem here as well? Limit of 0 is 0. Limit of this thing is 0. Limit of this goes to 0. That we actually did use that for sequences. Now the series is a little bit different, but basically the idea is about the same as far as comparing them. So with comparison tests, we set it up. All we have to do now is determine whether this thing converges or diverges. Let me make another point for you here. If this were divergent, would it tell you anything about this?
No.
If this is convergent, would it tell you anything about this? So we want to see if this is convergent or not. Is it? Oh, you got to show it to me. You got to show me. So let's talk about the series of 1 over 2 to the n. Tell me how that thing is convergent. Tell me why. And don't just say, well, if I take the limit, it's 0. You can't do that.
N is always increasing.
Say what now?
N is always increasing.
That's true.
So series is decreasing.
Explain that.
Or you can make the one to the n, the whole thing to the n power, and then take out 1/2.
Okay, so if I did this, is that still true? Guys, remember, you're not trying to reinvent the wheel here, right? You're trying to base these on series that you already know the conversions for. That's why I put it at the very beginning. Base it on a geometric. Base it on a p-series. Base it on a harmonic series. Base it on one of those things. Does that make sense to you? You can do the integral test for some of these, and that would work, sure. But it's easier if you base it on things that we already have, if you can do that. Quick head nod if you're okay with this so far. So we go, okay, cool. Well, we know that our terms are positive. We know that our terms, term by term, this is going to be less than this one. Now, this is great news for us, because we know something about the series of 1 over 2 to the n. The series of 1 over 2 to the n is the same as the series of 1/2 to the n. Oh, that's fantastic news. Why is that fantastic news? What type of series is that?
Geometric.
Now, because it's geometric, we can immediately determine whether this thing converges or diverges. Now, what I told you a long time ago, a few lessons ago, was that this and this have to match. Now, that's true if you need to find the sum. Does that make sense? Are we finding the sum of these series? No. So, do I care? Not really. I don't really care. You can, but notice that if I pull out a 1/2 to match my powers, if I pull out a 1/2 to match my powers, remember that whatever this is, you have to match it. 1 minus 1, 2 minus 2, 3 minus 3. If you were to find the sum. Because remember what the sum of the geometric is. It's A, that's your first term, over 1 minus R. I've already covered this. You can refresh your memory on that lesson as you want to. But since we're not finding the sum, it doesn't really matter as far as convergence goes. The reason why it doesn't matter, once you have this to a power, I don't care how many of those factors you pull out. That 1/2 ain't changing. Does that make sense? So all we're really looking at, not really the A, don't really care about it. What I'm worried about is the R. How much is the R? Absolute value of R is 1/2. That is less than. Remember that if we have the R, absolute value of R less than 1, tell me something about that geometric series.
Convergence.
That's perfect. So, because this is a geometric series with R is less than 1, absolute value of R is less than 1, this thing is convergent, or this converges. I'm hoping that you understand the reason why I'm not matching my powers. Do you understand why I'm not matching my powers?
We don't have to use
You're
sums.
trying to find the sum.
Not trying to find the sum. Don't really care about it. Okay, so let's refresh, because on your test you are going to have to find the sum, okay? If you did have to find the sum, would this be good enough?
No.
No. Now you could do this. Remember I gave you a shortcut. I said if you had to find the sum, you just think about what your first term would be. Your first term would actually be, if I plug in 1, your first term would be 1/2 over 1 minus 1/2. Does that make sense? That's how you do it really fast. No matter what that is, even if they don't match, it's your first term over 1 minus R. Not a big deal. If they do match, well, you get to use your A. It's A over 1 minus. A is your first term. Always you can take your first term over 1 minus R. It's not a big deal. I covered it in a previous lesson. You can go back and check that. Now let's keep going with our current problem. So we start here, we go cool, positive, less than 1 over 2 to the n. That's a geometric series. That thing has an r of 1/2, which is less than 1. It says that this series converges. Tell me something about the series that I'm given there.
It also converges.
Why?
Because it's less than 1 over.
Very good. The series we're given is less than or equal to some series that converges. By the comparison test, that means that this series also converges. Is it still making sense to you? Is it interesting to you? It's similar to what we've done before. I think it's kind of interesting, kind of fun. Tell you what, we'll try, we'll do one more and we'll talk about something slightly different. Would you like to try one? I'll give you about 2 minutes. Let's see if you can manage to figure this one out. If not, no big deal. So here's what I'm asking you. I'm asking you to firstly determine whether these terms are all positive. You have to show that. So the comparison test works when both of our series have positive terms. So show me, like this, that our terms are always positive and make sure that you're right. Notice that this does not start at 1, this starts at 3. So show me that we have positive terms. Nextly, determine what is going to work here, whether this should be bigger than or smaller than a given series. Remember that if it's smaller than a given series, that series must be convergent. If it's bigger than another series, that series that you're basing this on has to be divergent. So pick the correct one here. See if you can do it. Tell me something, are all the terms here positive? Did you see why we had to do n starts at 3 and not n starts at 2 or something? If we said that n starts at 2, we'd have something undefined. If we said n starts at 1, we'd have a negative and then something undefined. So we said 3, so we get something that is positive. So okay, so yeah, all the terms are positive. Now, next up, what is this going to be based on? What's a good series for us to base this one on? Try to figure out whether it's divergent or convergent. What is it?
2 over 2 raised to n.
Do you remember me saying that when you have a constant like that, that's the thing that's holding us back typically? This is what's holding us back right here. So we have 3 to the n over 2 to the n minus 4, and we have 3 to the n over 2 to the n. Check it out. Here's how you figure this thing out. Would you be able to tell me convergence or divergence for this guy?
Yes.
Okay, cool. Specifically, what would you be able to tell me?
It's divergent because it's
Okay, so we're going to get to a divergent series right here. Now, this one would have to be greater than or smaller than this one to show also divergence.
greater.
So we got to figure it out. Is this bigger than this?
It's
This is this one?
no.
No, heck no. If I take a denominator and I subtract 4 from it, it's going to make it bigger than my starting fraction. So basically it says this fraction is always greater than this fraction. My denominator is smaller, therefore my fraction is larger. Show of hands, feel okay with that one. Are you sure? Okay. Do you guys see the point of trying to do this? We're saying, hey, you know what? This is always bigger than this series. If I sometimes possibly equal, who cares? So if this series if we can determine that this series diverges, then we can show that this series diverges as well. how am I supposed to write this series? What should I do with it?
We may have that
Turn it into geometric.
Yeah, it looks just like a geometric series. That's great. So we'd have 3 halves to the n power. Remember, the idea is base your given series on something that you already know the conversions for, whether it's geometric, whether it's a piece series, whether it's harmonic series, one of the ones that we already know. So for us, we're saying, man, you know what? This thing looks a whole lot like, if I got rid of that constant, it would look a whole lot like a geometric series. So let's get rid of the constant. So if I get rid of the constant, what that means is I'm basing that on something without my -4. Well, it's going to be bigger than 3 to the n over 2 to the n without that 4. That's the idea. Since I know that this is geometric, that's why I chose that one, guys. I'm not picking something out of a hat. I'm picking something that looks really similar, that I know the conversions for, or divergence for. In our case, I know that that's a geometric series with r equals 3 halves. So we'd state this is geometric. This has an r with the absolute value greater than 1. Specifically, we'd probably write it this way. Absolute value of r equals 3 halves. That's greater than 1. Tell me something about a geometric series when your r is greater than 1 in terms of absolute value. Notice these are not arbitrary statements. You state it is geometric. You state that the r is 3 halves. Absolute value of r is 3 halves. It's bigger than 1. Therefore, this geometric series diverges. Now, is it going to be a problem that this doesn't match? No. Could you make it match?
Yes.
You could. You just pull out 3 halves to the third, and you'd have 3 halves to the n minus 3. Not a problem. Why aren't we doing that? This sum is not going to be the same as the sum. It's saying that this is always bigger than that. So I don't even really care what the sum is. It's divergent anyway. Why would I can't find the sum here. So I'm not really concerned about the sum, but if you're wondering why in the world are you not matching these up to an n minus 3, it's because the convergence or divergence will not, I said this one time, this is kind of an important note that you have down somewhere in your memory banks. Remember that convergence or divergence will not change if I add or subtract a finite number of terms. Do you remember that? The convergence or divergence will not change if I add or subtract a finite number of terms. The sum will change. Yes, the sum will change, but not the convergence or the divergence. So basically, this right here, look at the board please. This right here has the same convergence or divergence as this does. It has to, because all I'm doing is adding to it 3 terms. Or from here to here, all I'm doing is subtracting from it 3 terms. Does that make sense? Therefore, if this one this one diverges, I'm subtracting 3 terms. This one also has to diverge. Don't care that I can't find the sum. We're not worried about that anyway. We're not finding the sum here. What we're doing is finding out convergence or divergence. Now, let's go one step further. So because we know that my series is bigger than a given series for which I know divergence, tell me something about my given series. And that's exactly how I want you to write it. I want you to start with a given series. I want you to base it on something you know convergence or divergence for. Typically, you kind of have an idea in your mind, hopefully you do, before you start this. Like for here, I'm thinking, you know what? If I cover that up, that's going to be, oh, that looks like a geometric to me with r equals 1/2. If I cover this up, man, that looks like a geometric with r equals 3 halves. So I'm saying, okay, I'm going to try to make this smaller than a series that converges. I did it. Looks like a geometric. It's smaller than a geometric that converges. Therefore, my series converges. Okay, this one, it's bigger than a geometric that diverges. Therefore, my series also has to diverge. This is the case where a sub n is smaller than b sub n. It's forcing it to converge. This is the case where a sub n is bigger than b sub n. It's forcing it to diverge. Show of hands if I explain this well enough for you guys. Questions?
Could we have just skipped all this work if we did the limit test?
Limit comparison test?
Yeah.
We're going to in a minute. What do you mean limit test? It's like the divergence
just
test?
take the limit of that original thing and then go to infinity.
Yeah, you could have. But you didn't stop me. You should have. But you didn't.
thought you were trying to make a point, so.
I am making a point. I did make a point. But if you do, the first thing you should always do is what? I've said that every problem except for this problem, right? Because I was making a point. But if you did that, well, you have a fraction that's bigger than 1 raised to infinity. It's going to go to infinity. It's not going to go to 0. This would fail the divergence test. It would not equal 0. It would be divergent. Does that make sense? You can stop right there. Good catch. Let's try one more. Any other questions before we continue? You guys are awfully quiet today.
That just blew my mind, honestly.
This one?
The limit little comment.
The divergence test.
After I let it soak in. Oh yeah.
Now, doing this appropriately would take a little work because you can't just start with 3 to the n over 2 to the n minus, or without the minus 4. So you'd probably have to do the L'Hopital's and say this is infinity over infinity to get rid of that 4. So you have ln 3 to the n, over ln 2 times 2 to the n. Then you do it. Then you go ahead and say that's a constant. So pull out the ln 3 over ln 2. Have a limit as n approaches infinity of 3/2 to the n. And then we think, okay, this is a fraction that's greater than 1. True? Fraction greater than 1 being raised to the infinity power. That's going to grow and grow and grow and grow and grow and grow. This equals infinity. Therefore, this does not equal 0 divergence. That's what you were talking about, right? And you could also show it that way. So this is a twofer. We could do divergence test and it fails it. Hey, cool, no problem. It's not equal to 0, therefore our series diverges. Or you can show it this way. Honestly, for me, they're about the same level of difficulty, but you should be checking the divergence test first. That was a great point. Show of hands if you understood both of these. Good deal. Okay, now we'll do one more.
One more.
Well, that wasn't one more. That was the same one. So one more. Okay, I'm going to go kind of quickly through this one. So first thing, are all of our terms positive? Yes, no?
Yes.
Cool. Now, what's the problem on our series that we can't do what we want to do? What's our problem?
The +1.
The +1's a problem. So let's base this on a series without the +1. Because I don't want the +1. The +1's the problem. Is this series greater than this series, or is our given series less than our series that we just made?
Less than.
Less than. For sure. Less than. So far, so good? Okay, now here's the issue. If I do the series of 1 to infinity of 1 over the square root of n, do you understand that that's the series from 1 to infinity of 1 over n to the 1/2 power?
P series.
Tell me something about that.
P series.
P series, very good. What's the P? That's less than or equal to 1. Tell me something about a P series where the P is less than or equal to 1.
Divergent.
Now let's go back to our original series. We have a P series right here where the P is less than or equal to 1. This series diverged, right? What's it tell you about my given series?
Nothing.
Crap, why not?
It's greater than.
This is the time where you have b to the n and you have a to the n, and I say, hey, look at this. B to the n diverges. What do you think about this one? I don't know. It could converge. It could diverge. I don't know because it's not being forced anywhere. That's this guy. Okay. Don't be this guy. Well, this is the only thing that we could do. I mean, we can't make this smaller than a series that converges because we don't know what that is. We don't know what's gonna be. We don't know anything about this. The only thing that we could do is base it on this immediate one. This one that says, okay, we know for a fact that this is less than 1 over the square root of n. We know that for sure. But we know that this thing diverges. If that diverges and our series is less than this one, it's inconclusive. It's not a good test for us. That's the only thing we could do, but it wasn't a good test. Now, the point is we don't just stop here. We have something else that we could do. The other type, by the way, we didn't test this, but hopefully you did this in your head. Could you do the divergence test with this? Limit of this guy is 0, so we know we should have moved forward with it, unlike the last example. So if ever we can't just use a basic comparison test like the ones we had, what we had works great if your series is less than something convergent or more than something divergent. Does that make sense? If we're less than something divergent or more than something convergent, it doesn't make any sense to do that. We have another test for that. We're going to talk about what's called the limit comparison test. Here's the idea for the limit comparison test. If the series of a sub n and the series of b sub n have all positive terms, and here's the big part, okay? So positive terms, we had that from before, right? That's for any of these comparison tests. They have to both have positive terms. And the limit of a sub n over b sub n exists. Not exits. Sorry, exits. Leaves the room. It just gives up. Exists. And here's what we know. Then either both series converge or both series diverge. They're tied together so closely that one is a predictor of the other. And that's what the limit comparison test says. You could probably think of it this way. You think, okay, well, if this exists, think about this. Think about this. If this limit exists, this is a ratio, right, of one series, the terms of one series over the terms of another. If the limit exists at some point as n approaches infinity, that means that those terms are so close together that it doesn't really matter. Does that make sense to you? If they're so different that it does matter, that thing's going to go to infinity or negative infinity. Probably infinity, because they're all positive terms. But that thing would go to infinity. They would be so different. Does that make sense to you? So we say, okay, cool. So if this limit exists, then either both series converge or both series diverge. So again, I'm not going to write this down, it's the same idea. So we're going to compare our given series to a series that we know the convergence of. And then we're going to take a limit. That's the idea. Would you like a proof of this to prove that this is actually true?
Yeah.
Okay, so here's the proof. Let's suppose that this limit exists. If this limit exists, then the limit as n approaches infinity of a sub n over b sub n would be equal to some limit. True? By definition of what a limit is, what this means is that absolute value of a sub n over b sub n minus L would be less than epsilon. Remember those epsilon delta proofs? You loved them, right? Woo! That's what a limit, that's the definition of a limit. It means that the different, it's a very simple idea, it looks really confusing, it's a very simple idea. It means that if this limit exists, then the difference between those, this fraction, well, whatever your function is, between this function and your limit, the difference between those in absolute value is less than whatever you say, it can make it smaller. That's what it means. So you give me 0.0001, I can show that this difference is smaller than that. That's what the definition of limit is. It says the difference between them is so negligible, it doesn't matter what it is, even if you give me epsilon, a really little number. Does that make sense? Are you sure? Okay, so this is by definition is true. So if this is true, then for certain, I can multiply by L and it's still true. Since L is a number, it's still true. Well, we're going to use that. Because we have an absolute value inequality, we should know that we can solve this inequality, well, we can manipulate this inequality by doing negative absolute value, epsilon, that's the absolute value. Negative epsilon L is less than A sub n over B sub n minus L, which is less than epsilon L. Well, that would have to be true. That's how absolute values work. Absolute value inequalities work this way. You go, okay, well, if I make that negative, this is bigger than that. If I leave it positive, this is smaller than that. It's now a double inequality. We're just going to solve for this. So what we're going to do is we're going to add L to both sides. If I add L to both sides, I get L minus epsilon L is less than A sub n over B sub n, which is less than L plus epsilon L. Almost done. Last thing I'm going to do is I'm going to factor and I'm going to multiply it by B sub n. So we factor out the L, no problem, it's 1 minus E, 1 minus epsilon. Factor out the L, it's 1 plus epsilon. Multiply by B sub n on all three sides. By the way, we can do that because B sub n is what type of a number, what type of terms? They're positive. It's not going to change my inequality. So this is all based on that the B sub n has to be positive terms. So we can do that. It does not change the inequality. Not sure if you understand that idea. Okay, so it's positive. We're all good as far as inequality is concerned. Well, here's the idea. Here's where this comes in. Do you understand that that's a constant? Easy, epsilon is going to be some number, right? Add 1 to it, still some number. Multiply by L, it's still some number. So the convergence of B sub n is not affected by what this is. Likewise, the convergence of B sub n is not affected by what this is. So think about this. And this proves both of them. This is kind of cool. If the series B sub n converges, A sub n is less than that series. Do you see that? Okay, you're not really with me, huh? Are you with me?
Yes.
Kind of, sort of?
Yes.
Do you see the comparison test out of this right now? If B sub n converges, A sub n is less than that. If B sub n diverges, A sub n is bigger than that. So just based on whatever we're looking at, if B sub n converges, no problem, A sub n converges. If B sub n diverges, A sub n also diverges. That's the idea. Show hands if you understand the idea. That proves this guy. That proves this theorem here. So I'll write that real quick and we'll be done. If B sub n converges, since A sub n is less than that, and this does not, by the way, this is a constant. It's not going to affect the convergence of our series. It'd just be our series multiplied by whatever that constant is. If B sub n diverges, A sub n also diverges. Now, of course, I haven't done an example with this, but we're going to do that last example I had with our limit comparison test. So here's the whole kind of put everything together moment for you. The first thing we start with all the time, is what?
Limit.
Divergence test. Just take a limit. If it doesn't equal 0, you're done. It diverges. After that, start thinking about easy stuff. Okay? Is it a geometric? If it's geometric, do it. Goodness sakes. Is it a p-series? Is it harmonic? If it's not one of those things, then we start talking about, okay, well, can I do an integral test with it? Maybe I can. If it's positive, continuous, decreasing, integral test works real nice. If it's not one of those things, or maybe it's easier to do this, You go, okay, well, at this point I think, well, now with the comparison test, is this always smaller than a series that is convergent, or is my given series bigger than a series that's divergent? If it is, man, we're done. If that's not the case, if you go, man, and now I have something that's smaller than divergent or bigger than convergent, I can't really use a comparison test straight up, then what we do is we go, well, maybe a limit comparison test would work. We'll say, this one's so close to the other one, so close, they'll take a limit of the ratio of them. If I take the limit of the ratio of my series, then if that limit exists, my result will be the same for both my series. They will both converge, or they will both diverge. Does that make sense to you? Question?
With these tools, can we do anything, or are there some that are just, they need?
Can I do anything? No, there's other things, other techniques I'm going to show you. You can do a lot with them, I'll put it that way. Okay. All right, so let's wrap up this example. So what we learned was that oftentimes we can't use the comparison test just like it is. For instance, when we tried the comparison test with this particular series, we said, sure, the terms are positive, that's fine. Sure, it's less than 1 over the square root of n. However, because 1 over the square root of n, that series diverges, and it's bigger than the given series that we want to show convergence or divergence for, that doesn't do us a whole bit of good. Because, well, if this is bigger than the series and this diverges, it's not forcing this one to do anything. Therefore, the comparison test by itself won't really work. We need something that, if we have our given series smaller than a series that converges, that's good. Or bigger than a series that diverges, that's good. But smaller than a series that diverges doesn't do us anything. So we invented this new thing. We said, all right, well, if the comparison test doesn't just straight up work, let's try the limit comparison test. So we said, all right, no problem. Let's compare these series in a ratio, no problem, just some sort of fraction here, and let's take the limit as n approaches infinity. If that limit exists, what that means is that these series are so close together that the ratio exists to some number. They're so close together that if one converges, the other one's tied to it, and if one diverges, the other one's tied to it. So basically what we do is we compare a given series to one that we know the convergence or divergence for and take the limit of it. It's not a straight up comparison test that's saying it's always less than or greater than, because that won't work in this case. But if we take the limit and we say, all right, tell you what. By the way, A sub n is always your given series, always what you start with. B sub n is always something you're trying to base your series on that you know the convergence or divergence for. So we say, all right, our A sub n here is 1 over the square root of n plus 1 over something that looks a whole lot like our series that we know the convergence or divergence for. So namely, we say, all right, well, let's compare it to the 1 over the square root of n. This thing's going to behave a lot like this. That's where we're getting this from. Are you guys okay with this so far? Show of hands if you are. So it's looking just like this, right? Only we're not doing a comparison test as it's always less than or greater than. We're doing a comparison test as far as the limit's concerned. That's why it's called a limit comparison test. We're taking the limit of this comparison. So far, so good? Do you know how to do limits?
Mm-hmm.
Of course you do. So we'll just make this thing simpler. Since we have a complex fraction here, let's make this, we'll reciprocate and multiply 1 over the square root of n plus 1. Excuse me.
Bless you.
Thank you. Times the square root of 1 n over 1. All right, well, that's going to give us a limit as n approaches infinity of the square root of n over the square root of n plus 1. Tell me something about that. What's the limit?
Infinity over infinity.
Okay, tell me what you could do. You could if you wanted to. Now, notice that you have the same thing over the same thing, right? So that might be an issue for you, I don't know. Maybe something a little bit easier, something that we think... Can't split this one up because our denominator can't be split up. So we can't do that. What we could do is maybe just divide by the largest power in the denominator, which is what we typically do with these things anyway. So if we do divide by the largest power in the denominator, I think Frank said that in the back. If we divide, we're going to get the square root of n over the square root of n, that's 1. We're going to get the square root of n over the square root of n, that's 1. We're going to get 1 over the square root of n. And that saves us a whole lot of time. We don't have to worry about L'Hopital's rule. So don't skip some of the easy stuff when you're doing these limits. Oftentimes, it's a lot easier to just divide by the largest power in the denominator if you have something that's rational, like a rational expression, or even square roots, things like this. Almost like polynomials. You guys okay with that so far? So tell me what the limit is. What's the limit of 1? What's the limit of 1? What's the limit of 1 over the square root of n as n approaches infinity?
Zero.
Bam. How much is this limit? Okay, now, please listen carefully. Here's what this whole thing means. What it means is that these two things were so close together that our limit existed. It also means they're so close together that if one converges, the other one has to converge. And if one diverges, the other one has to diverge. So please do not make the mistake of doing this. Do not make the mistake of saying, hey, the limit exists, therefore it converges. That is not what we're talking about. We're talking about in the limit comparison test is, since the limit exists, they will both have the same result. They'll both be convergent or they'll both be divergent. That is why you compare your given series to one that you already know the convergence or divergence for. You say, hey, you know what? I know this one. What is that? Is that convergent or divergent?
Divergent.
That's divergent. Why?
The P series.
Very good. And the P is? So it's a P series with P less than 1. True? That's divergent. So what this says is, this doesn't mean it's convergent. This means that this thing is going to have the same result as what you're basing it on. That's what it says. So if the limit exists, we go, okay, well, since the limit exists, since they both have positive terms, which they both do, we already checked that earlier, since the limit exists, and the series of 1 over the square root of n diverges, the series from 1 to infinity of 1 over the square root of n plus 1, tell me something about that one then.
Divergent.
Also diverges. So, we say, all right, the limit exists, they're tied together so closely that they're going to have the same result, either both converge or both diverge. A limit existing here for the limit comparison test does not automatically mean convergent. That's not what it means. What it means is that whatever your series is, and whatever series you're basing that on, both converge or they both diverge. If you know one of them diverges because this is a P series with P equals 1/2, then you know this one also diverges because that limit existed of that ratio. Question?
I'm kind of confused. When we do limits and say we had 1 over x squared, took the limit as n approached, or x approached infinity, we say that that's 0, right?
True.
But then we do like series, and it's like a P series like that, we say that it converges.
The P series does converge.
But does it just converge to like 5 or something like that, where it would be infinity anyways, or I don't...
Well, the P series converges, but a series is different than just a straight up limit. Now, we check a straight up limit on these series just to see that the sequence is going to converge. So try not to get confused with sequence versus series, okay? What we do immediately with the divergence test is say, hey, look at your sequence of numbers. This is the divergence test. Does your sequence go to 0? Yes, it does. That means that ultimately for our series, what we're adding up are values that are 0. Now the series itself is not going to go to 0. The series itself is going to add up a number of terms. I don't know what that's going to add to in a lot of these things. I do if it's geometric, because we can find the sum of that, okay? But I don't know what that's going to be. So when we're taking a limit here, we're not actually finding a sum. We're not actually finding out whether it's equal to 0 or not. We're not actually finding out basically anything besides these things are really closely tied together. That's what the limit comparison test does. It says these things are really closely tied together. Does the limit have to equal 0 for this to work? No. No, it just says that it has to exist. It can't be infinity. It can't be does not exist. Okay, it's got to exist to be a number. If it's 0, cool. If it's 1, cool. I don't care what it is, as long as it's a finite number. That means these are tied together, and the divergence or convergence will be the same between our two series. Now, when we're taking a limit of a series like when we did the limit of this one, again, what you're just saying there is the divergence test says the sequence from which your series is built has to go to 0. Because ultimately, you got to add up terms that are close to 0 for it to make no difference. Does that make sense? If we would have had something like n over the square root of n, we'd add up terms that ultimately would lead us to infinity. That means that our series would go towards infinity as well, and we would not be able to add that together. We would not be able to find a series that converges. So convergence for a series just means that ultimately you're going to be adding up terms that are 0, so ultimately you'll come up with a sum that is not infinity, that is an actual finite number. Did that clear something up for you?
Yeah.
Okay. I know it's a little confusing because we talked about sequences, right? And now we're talking about sequences kind of, but we're adding the terms together. So some of the things are along the same line. And now I'm bringing up limits again and saying, yeah, the limit doesn't have to equal 0. It doesn't. And it doesn't mean that if the limit exists, we're getting convergence. Doesn't mean that if the limit exists, we're getting divergence. You have to read the problem. You have to say, hey, this thing, if it exists, these two series will have the same outcome. Whether one's divergent, the other's divergent. Where one's convergent, the other's convergent. So it's a little different idea. We're using a limit here not to show convergence or divergence. We're using a limit here to show that they have the same convergence or divergence. And I proved that theorem last time. Okay, anyway, I'm going to move on here a little bit. I'd like to get a couple more examples out of you. See if we can do this one. Are there any further questions? That was a good question. Thank you for that one. Any other questions before we move on? Did this make sense to most of you? Did this make sense to all of you? How many people did it make sense for? Feel okay with that one? Iffy? Are we okay? Question?
So just to further clarify, if this limit were to approach infinity or some
Yeah.
abstract number like that, then what
Then
would
you
happen?
can't say a thing about it.
Then, okay, we'll just.
You might try maybe a different series.
Okay.
Okay?
Yeah,
Thank
Now,
you.
for us, usually we're going to pick them so that they're really close. I'm going to show you how to do that right now. So maybe this will clear up your question. Question? Okay, 1 and then 2.
So A sub n is the one that's given, and B sub n is the one that you're using, right?
Always.
Okay.
Question?
Do you want us to answer it like that with the, like a sentence?
I would
describing
love it if you guys would answer it like that. I'm guessing some of you won't, but I would love it if you would answer it just like that, because that is literally what the answer is. It's saying because the limit exists, because the series here diverges, because it's a p-series. You have to state things like this, okay? You can't just say, it diverges. You got to state why. You got to show me your thinking here. Much of this is not going to be just math work. Much of it is thinking, reasoning. Like, well, this is a divergent series because it's a p-series because p equals 1/2. Okay, cool. How does that relate to what we're doing? Well, because the limit exists, it says that they're going to have the same result. They're both going to be convergent or divergent. And since one was divergent, the other has to be. That's the idea. Any other questions? Those are all good. Let me show you another one. Last chance. I waited this time. I was nice. And you go, man, what are we going to do here? Well, listen, we don't have to have a series that's exactly the same. That's not the idea here. We have to have a series that behaves kind of like this one that we know the convergence for. So, here's what we do. When we're coming up with these, especially when you have something that's rational or semi-rational, where you have almost polynomials or square roots of polynomials, listen, do you guys know anything about limits as n approaches infinity? Do you know that with polynomials, the limit is dictated by the behavior of your very first, your leading coefficient, your leading term, your leading term? Did you know that?
Yeah.
So think of the end behaviors of these functions. So the end behavior of this function, I don't even care what that is. The end behavior is going to look a lot like 2 over n squared. Does that make sense? The end behavior of this, does that 3 really matter as far as the end behavior goes? No. This is a whole lot like the square root of 4 n to the 7th. That's really what we have there. That's the end behavior. So when we're doing these, we're going to compare this to this one. Why? Well, this is going to act really similar as n approaches infinity. Now, are all the terms going to be the same? No, but as we get towards infinity, these terms are going to be really close to that one. So the end behaviors will be very close. So what I want you to do is think of end behaviors. Basically with polynomials, that's really easy because that's just the leading term. That's what a limit is n approaches infinity, or x approaches infinity, is just the leading term. The term with the largest power. That was it. So let's be kind of nice about this. Can you simplify that? Hey, that's why this thing's going to be nice, because if we simplify this, we will find out what the convergence or divergence is of it. So let's do it. How do I simplify it?
Squared over n squared n.
Say what?
Pull the 4 out and then.
Pull the 4. Okay, so 2n squared over 2n to the 7 halves. We could do that.
Yeah.
Can I keep going? How much is it? 2's gone. Yeah, okay, that's good news. What about n squared over n to the 7 halves? Can you do that?
1 over n is 7. Oh wait.
Then pull the check.
3 halves.
Reciprocal and then multiply.
Bring it up.
That's what I meant.
N to negative 7.
Let's see, this would be 4 halves minus 7 halves. That's n to the negative 3 halves, or we get 1 over n to the 3 halves. We get 1 over n to the 3 halves. You guys okay with this so far?
Yes.
Are you sure? You should be, because that's freaking just some algebra, and you should be okay with it. Now, tell me something about this series. Tell me something about that series.
P-series.
That's a P series. What's the P?
3 halves.
So this is P series with a P equals to 3 halves greater than... Tell me something about a P series with a P equals 3 halves greater than 1. What do you know?
Convergence.
That's convergent P series. Now, let's think about what the limit comparison test is going to do for us here. So, we probably already would have done the divergence test. Hopefully you would have done that. Now, the limit of this sequence here without the series, the limit would be 0, we're good to go. It says we might not be divergent. Then we go ahead and we think, well, is it a straight up P series? Is it geometric? Is it any of these things that we can do? Is it integral test? Is it a comparison test? I don't know, it looks pretty hard for a comparison test. Can I do a limit comparison test? Yeah. Yeah, think of the end behaviors. End behavior would look like this guy. This guy is a convergent P series. So what we're going to do now that we've determined that this is a convergent P series, or even if it was a divergent P series, we compare this as a limit as n approaches infinity. What's going to go on the numerator of this ratio? The original one. Very good. Well put. So the original series, that's our a sub n. Over what?
The end.
Say what now?
1 over the end. To
The end one. So
halves.
this one. You could even use this one. Whatever you want. Now, that's fine. I don't think it really matters which one you use. We do them basically. I'd use that one because it's nicer. Basically, and you can do these a couple ways, okay? Basically, what I like to do, I like to find out what I'm going to compare my original series to. I like to simplify that as much as I can because they all should be simplified because basically you're getting rid of everything but the leading terms. Did that sink in? That means they're all going to simplify. Hello? You're getting rid of everything but leading terms. Should be just one term over one term. You can simplify that. I like to find out whether it's going to converge or diverge first. I like to have that in the back of my mind. Then I like to compare it with the simplest form. That should make sense, right? That way I don't have to re-simplify in my problem. Well, this is a whole lot easier to deal with than that one is, isn't it? So why would I put that back in? I'm going to use my simplify. Tell me the next step. What would you do? Multiply by reciprocal. We could do that. Are you starting to notice all the algebra you're going to do? So we'll have 2n squared plus n over the square root of 4n to the 7th plus 3 times n to the 3 halves over 1. Now I'm going to move over here. What now?
Distribute the n with 3 halves.
Yeah, okay, we can do that.
2n to the third plus n plus 2x to the 5 seconds.
2n to the what now?
The 2 cancel out. Oh wait, no, never mind. Oh, 7 multiplied by 7.
You guys are going to make me start drinking, aren't you?
Sorry.
I'm dead.
I need to drink, guys.
Just punch more.
I want to punch more papers.
Can we just pull more ends out? Because I think that's what we end up doing anyways.
So 5.
We add
7 halves.
threes.
7 halves.
Yeah.
7 halves.
It's the 7 halves.
God, put me on the spot. Now, anyone else?
2n raised to the 7.
You guys figured it out. You gotta make me.
Well, it'll be 2 over 2
I'll
plus 3
figure it out.
over 2.
You better be able to
so
figure it out.
3,
Let's see.
4, 5 over 2.
Okay, last time I checked. Yeah, last time I checked, it was 7 halves. Do you know what you do when you multiply common bases? You add
You add
exponents.
them.
Okay.
You gotta get.
Plus how much?
5 over
5 over 2.
Over nasty square root. Don't do a L'Hopital's rule. Don't do that. Just divide by the largest power in the denominator. So if you divide by the largest power in the denominator, here's how you figure that out. You cover up all but the leading term. That would be the largest power. So cover up all but that thing and write that as a power. So we're going to divide by by what?
7 divided by
And to the 7
N
halves.
to the 7 halves. Divide by n to the 7 halves. So we're going to divide by n to the 7 halves over n to the 7 halves.
Works out.
I want you to understand that these are equivalent. Do you understand that they're equivalent? One we've written as rational exponents, one we have as radicals. Now, please listen carefully. You don't always get to do this just like it is. You have to verify that your radicand, the inside part, is actually positive. Because this is positive, we can make that straight up move. Does that make sense to you? So that we're good to go. So if we divide this, we're going to have a limit as n approaches infinity of 2 n to the 7 halves over n to the 7 halves. I'm going to show you every step here. Plus n to the 5 halves over n to the 7 halves. All over. Big square root, because that has a square root, that has a square root. We'd have 4n to the 7th over n to the 7th plus 3 over n to the 7th. I want to make sure that you guys understand that we are not multiplying here, we're dividing by each of these terms, okay? So it's getting divided, it's getting divided. That's why we have this over n to the 7 halves and over n to the 7 halves and over n to the 7th. Because we have 2 square roots here, we can make that one large square root over n to the 7th and over n to the 7th. Show hands if you feel okay with the algebra there. Let's simplify it. So we have a limit. N approaches infinity. How much does this give you?
2.
Plus 1 over what?
0. 2.
N. Over, this would be square root of 4 plus 3 over n to the 7th. Can we take the limit now that we got rid of all that stuff? What would you get? What's the limit of 2 as n approaches infinity? What's the limit of this as n approaches infinity? That goes to 0. How about the limit of this one?
0.
How about the limit of this one? What's 2 over the square root of 4?
1.
What's that tell you?
The limit exists.
The limit exists. That's what it tells you. It says the limit exists, which means that going back here, it says that what we have and what we compared it to will have the same result. If this one's convergent, the one we're given is convergent. If this one's divergent, the one we're given is divergent. Does this always tell you convergent or divergent? No. The first example, we had it existed, yet it gave us divergent. Now we have limit existed, yet it's going to give us. So the way we write this is,
So if limit exists.
since the limit exists, and the series of 1 over n to the 3 halves as n equals 1 to infinity converges, then we have the series from 1 to infinity of our nasty junk also converges. That's the idea. Do you understand the idea? Show of hands if you do. You feel okay with this stuff. Easy, medium, hard, different. Probably a little different. It'll get easier. The problem with all this stuff is that there's so much stuff. That's the problem with this. It's because some of this will get confused in your heads. And some of you will think back to the comparison test for sequences, forget about the limit comparison test here. Some of you will get confused with the divergence test, taking a limit of a sequence here saying equal to 0 and automatically think it converges. Some of you will think, well, since this doesn't equal 0, it must diverge. That's not what we're doing. You need to get the test straight. I know it's new, and there's a lot to it. There's a lot of stuff that we're doing. So I'm going to try my best to reinforce the ideas here. The ideas are you start with the divergence test, and you take a limit of this sequence from which your series is built. If it does not equal 0, you stop right there. Your series is divergent. Does that make sense? After that, you keep going with one of the methods that I've used so far. Geometric, p-series, integral test, comparison test, limit comparison test. There's several now. We do a limit comparison test, but you understand with the limit comparison test that if you equal any number besides infinity or does not exist, that means the results are tied together. Both converge or both diverge, not necessarily one or the other. Okie dokie. Would you like to try one more?
Yeah.
One more. Okay, one more. Any questions before I erase it? Are they kind of fun though? They're kind of fun, right? I enjoy them. It's totally different than doing all those integral stuff, isn't it?
Kind of like a puzzle.
You just got to get creative with picking a new piece of n.
That's why it's kind of like a puzzle.
It can be puzzling. Especially with this one. Let's start from the beginning. First thing, what would you do first?
Divergence.
You would do it. Let's pretend that we did it, okay? But you want to start there. Let's pretend we did it. Divergence test, it equals 0. What should you do? Keep going or stop?
Wait.
It equals 0.
Keep going.
It equals 0. What would you do? Stop?
No.
Keep going. Okay. What would you check here? Would you want to do integral test?
No.
Can you do the integral of that thing? No, probably not a good idea. Does it look like a p-series?
Nope.
Look like a geometric series?
No.
Look like something we could compare it to?
Yes.
Yeah, but not a real easy one, huh? Because I don't know that that's always less than something or always greater than something. So if it's not something easy like that, like we had with a couple of them that were nice, we go, well, maybe we want to try the limit comparison test. So let's try to see if this compares to something. So this compares to what?
Just get rid of an ln.
Well, here's the thing. You're going to get rid of part of it, right? But you need to keep the fastest growing part. First of all, I've been skipping a couple things. You do need to make sure that this has positive terms. And I'm kind of taking that for granted. That's not a trivial point. You do have to make sure that it has positive terms. Does this have positive terms?
Yes.
As long as n is greater than 1, yes it does. Because n between 0 and 1 here would be negative terms. Maybe. Well, actually I would for here. So we do have positive terms, but we need to check it. Now, if you're going to talk about end behaviors, that's what I told you, right? End behaviors of this one, that's going to be pretty easy. What goes on our denominator? Yeah, that's a piece of cake. End behaviors of this one can get a little tricky. What you want to do, you want to keep the fastest growing part. The fastest growing part will give you the end behavior. Does that make sense to you? That's why we keep the largest power, that leading term, because that's given us our end behaviors, the fastest growing or fastest falling part. Well, in our case, what grows faster? Square root of n or ln? Better, I don't know. Many of you are guessing right now.
Did you punch it into your calculator and look at the graph?
They're very similar.
Square root of n is decreasing as it gets larger. The ln of n gets bigger.
Untrue.
Square root.
They both increase.
Put some high number in both. and see which
Put some huge number in both of them. That'll prove everything. That's a great idea. Well, you can think of it as ln of n is an inverse of e to the x, correct? So if e to the x starts climbing real fast, ln is going to climb, but slower, slower, slower. Less of a pace than square root of n. Square root of n is the faster increasing one. Now, how do you show that? Here's how you show it. Maybe you consider f of x equals square root of x, and f of x, sorry, maybe g of x. Oh, I don't get confused on that. G of x equals ln x. The derivative is 1 over x. The derivative is 1 over 2 square root of x. You can verify that later if you want. Now, here's the whole point. This is kind of interesting to think about. Hope you're with me on this one. You guys okay on the derivatives, right? Derivatives tell how you're increasing in this case. They're both increasing graphs. It tells how you're increasing. So, whichever one goes to 0, whichever derivative goes to 0 faster, that's the one that stops increasing sooner. I'll say that one more time so it makes sense, okay? This is how your functions are increasing. Are you with me? They're both positive with n greater or x greater than 1. So this is how they're increasing. Since this shows how your graphs are increasing or your functions are increasing, whichever one goes to 0 faster is the one that stops increasing sooner. Did that sink in? Which one goes to 0 faster? This one does. That goes to 0 faster. So this goes to 0 faster than this. Therefore, f of x increases faster than g of x at the end. It will you can think of it as increasing longer, increasing faster. This is the basic idea. Does that make a little bit of sense to you? It's kind of weird, right? You're using a derivative to say, well, which one goes to 0 faster, which one slows its increasing behavior faster. Since this goes to 0 faster, this slows its increasing behavior faster than this one does. That's the idea. This will always be increasing at a faster rate than this one. Does that make sense to you? Okay. Don't just plug in numbers, please. I'm begging. Plug in 7. I don't know. No, don't do that. Okay. Actually, go through the math here. So, what are we going to pick for this one again? Is it going to be ln of n or square root of n?
Square root of n.
Yeah, it's going to be square root of n. Because this one is going to be the end behavior, the model for end behavior. Since this increases faster than this one at end behavior, we use that. Now, can you simplify it? If you have only one term over one term, you better be able to simplify these things. Let's simplify it. What is it?
N to the 1/2 minus 2.
So 1 over... Don't leave me hanging. Huh?
Is it 3 halves?
Yes, it is.
3 over 2? Or 1 over 3 over 2?
1 over n to the 3/2. Exactly what that is. Does that make sense to you? We have square root of n, that's n to the 1/2. 1/2 minus 2 is negative 3/2. We'd have 1 over n to the 3/2. Tell me something about that series. So we're talking about this compared to the series. I'm kind of admitting that, but this is what we're doing. This is what now?
P-series.
Same as last time.
It's the exact same thing. It's a P series.
I love P-series.
Me too, I really do. They're so easy. P series, P equals 3 halves, greater than 1. Tell me something about this particular P series which we are comparing our given series to.
Convergence.
Brilliant. So, tell me this. If we compare this to this and the limit exists, what do we know about that?
That it also
It also converges. Very good. What if the limit doesn't exist?
No, we don't.
Done. Can't do it.
That's something else.
So let's do our limit comparison test. So we start off with a limit as n approaches infinity of, what goes on our numerator, please?
Square n plus ln n.
Oh, that's going to be nasty. N squared plus 1, all over what? Over what?
Over n to the 3 halves.
Yeah, that's right. And then we start working with it. This is a limit as n approaches infinity of square root of n plus ln of n over n squared plus 1. That's a lot of n, dang. N to the 3 halves over 1.
That is a little bit.
That is a lot. From there, what would we do? Let's distribute. So if we distribute this, we get a limit as n approaches infinity of,
N squared. N squared.
Wouldn't it be n to the 5 halves?
if this was a 1 power, you'd have 2 halves plus 3 halves, it would be 5 halves. But this is a 1/2 power. 1/2 plus 3 halves is, that's n squared. Plus n to the 3 halves ln
Tuna was right.
n over n squared plus 1. Goodness gracious me, that's a lot of stuff going on. What's the next thing that you might want to consider doing? Would you try like a L'Hopital's right now or something? Is that a good idea? No. You get that plus right there. That's not a good idea because this would be infinity plus infinity. We don't know what that is. Okay, it's got to be indeterminate form for you to do a L'Hopital's. Now, I'll give you a caveat to that. You can do L'Hopital's on individual portions of this because you could split up parts of your limit. You could do that. We'll do that in a minute. So, what would you do? So let's divide by n squared. Everywhere. So this is a limit as n approaches infinity of n squared divided by n squared. Yeah, I'm going to write it out. Plus n to the 3 halves ln n over n squared all over n squared over n squared plus 1 over n squared, just so we see where everything's coming from. Limit as n approaches infinity. Oh goodness. What's this?
1.
Plus
ln over n to the 1 half.
ln of n over n to the 1/2. Exactly. This is 1. This is 1 over n to the 2nd. Can I have a show of hands if you feel okay getting down to that far on your own? On your own. Okay. What's the limit of 1?
1.
What's the limit of 1? What's the limit of 1 over n squared is n approaches infinity?
0.
So this is going to 0. What about that one? It's an indeterminate form. Why is it an indeterminate form?
Infinity over infinity.
Brilliant, exactly right. So, off to the side, then you can do this, it's okay. Here's why you can do it. You can separate this limit by addition. We can do a limit as n approaches infinity of ln n over n to the 1/2. This thing equals infinity over infinity. So we'll do, oh, what are you going to do with infinity over infinity again?
L'Hopital.
Love L'Hopital. He's much better than Lopi Short. Joking. That's a horrible joke. I get my sense of humor from my dad. Love you, Dad. I don't know if he watches these. He should. He really should. Give him something to do. He said he's working on his. Never mind. Don't watch that, Dad. So, what's a derivative of ln?
1 over n.
Derivative of n, that looks sloppy, doesn't it? N to the 1/2. What's a derivative of n to the 1/2?
I think 1/2 n.
One over-
No, 1/2 n to the negative 1/2.
That was a lot of.
Okay.
1 over 2.
Okay, let's do that. That's easier. Yeah, 1 over 2 square root of n, if my math serves me correctly. I don't think so. Is it a negative?
No, it's not.
I don't think so, because you bring in the 1/2, you take 1 away from the exponent, it becomes negative, that's a negative exponent, that goes to the denominator, so 2 square root of n. Let's go ahead and let's reciprocate and multiply. So we have, if we reciprocate and we multiply, we're going to have, what is that? Anytime.
1 over n times 2
2n,
root n.
yeah.
Reciprocate and multiply. So far, so good?
Yeah.
Yeah.
Okay, well, yes, but be smarter about this, okay? I should have taught you something, I know that I did. Before you start doing L'Hopital's rules again and again and again and again and again, simplify it. Simplify this thing before you go any further. Because right now you're going to be done.
Oh, yeah.
So don't just arbitrarily jump into a L'Hopital's before you simplify. We should have learned that a long time ago when it said, with L'Hopital's rule, before you do it again, you must simplify the fraction. And that goes without saying, hopefully, for you. So with us, this is going to be 2 over the square root of n. Yes, no? Tell me something about the limit as n approaches infinity of 2 over square root of n. What is it?
0.
Okay, so now we know this thing is 0. So we have a limit as n approaches infinity. Actually, we let it approach infinity. What's this limit going to equal? We have 1 plus 0 over 1 plus 0. How much is it? So our limit equals 1.
Do most of them come out to 1?
I can't say that. No. I don't know. It just depends.
Just coincidence?
So it's 1 over 1,
Yeah.
right?
So what?
So the limit of that is 1 over 1 because that indeterminate form approaches 0.
Right. You know, I'm going to go out there on a limb and say, yeah, they probably do, because if you're talking about n behaviors and you're saying they're very close, you have basically something over the same thing, so a lot of them should work out to 1. What's the next statement that you're going to make? Do you know the next statement you're going to make?
Since the limit exists.
Since the limit exists, so write that down. Since the limit exists, and
Some series of 1 over n to the 3/2 is convergent.
because,
P series.
Is greater than 1.
very good, then what do you know about our given series?
It also converges.
That's exactly what you should write. So, word for word, since the limit exists, and the series of 1 over n to the 3/2 is convergent by p series, p is 3/2 greater than 1, then, and this is the only part I'm going to write because I've ran out of room, then the series that we were given also converges. I should be a period. Also converges. Here's what I'm wondering. Does a limit comparison test make sense to you?
Yeah.
It's kind of a cool thing, isn't it? It's saying use the n behavior, make a limit out of it. It's just a ratio. Saying if the n behaviors are very similar, make a ratio. If that limit exists, then sure enough, they're both going to be convergent or both divergent because they model after the same curves, basically, at the n behavior. That's the idea. So we have a number of things now, and here's the wrap up. The number of things. First thing you always check for is, yeah, always take the limit of the sequence from which your series is stemming, okay? Just the terms. If it equals 0, you must keep going. If it doesn't equal 0, you're done because that whole thing is divergent, okay? After that, check for the easy ones. Don't make this stuff harder than it is. I would automatically check for geometric. Maybe I can make it. I would automatically check for p-series. I mean, that'd be a piece of cake. That'd be kind of nice. After that, I'd check for, if it's an easy integral, I'd do integral test, if I can do that. Or we could do now a comparison test. Like an easy comparison test would be kind of cool to do because there's less than something that's sometimes really easy to do. If that's not the case, we got to do a limit comparison test. So for some of these nasty looking ones, limit comparison test is the way to go if you can show what the end behaviors are appropriately. So for us, remember that was this whole piece right here saying, well, we want to stick with the square root of n and not the ln of n, because that is really the end behavior of that function. Does that make sense? That's the numerator of our sequence, as it were. After that, it's pretty straightforward. If a limit exists, you're good to go. Whatever series you base this on, compared it to, that's going to be also the result of your given series, whether it's convergent or divergent.